Okay, IPv6. IPv6 is a network layer protocol, layer 3. We use it to transmit data end to end across the network. So just like IPv4, we're worried about getting it from the source location to the final destination, and we do that by delivering it across many hops, usually across many routers, and each router will route that traffic based on its destination IPv6 address and then deliver it locally at layer 2 using the MAC addresses. So the layer 2 stuff all works the same with IPv6 as far as delivery goes. Layer 3 stuff is what we're going to talk about today. IPv6 was defined originally in RFC 2460 in 1998. There are some subsequent RFCs that have updated it, but I didn't list those for you. You can go look those up if you want. The main changes in IPv6, which we'll talk about all these individually, we expanded the addressing capability. We made the header format better. We improved support for extensions and options. We added a flow labeling capability, and we added authentication and privacy capability. So the main reason we needed IPv6 when it was developed was because we were running out of IPv4 addresses. We've done some things we'll talk about later on to stem the tide on that, but that was the main motivator to change the protocol to have a new protocol. So the IPv6 addresses are 128 bits in length, which is 4 times longer than IPv4 addresses. So that gives us, I've read things that say that's enough addresses for every square inch of the earth to have 1,000 addresses or something ridiculous like that. So that's a lot of addresses. We should never run out of IPv6 addresses, but with the Internet of Things, you never know. There'll be another podcast later on where we talk more specifically about IPv6 addresses. Since they were updating the protocol, right, our IPv4 header has a 32-bit field for source address and a 32-bit field for destination address. So since we were updating the header anyway, we decided, I shouldn't say we, I didn't do it. It was decided that we should go ahead and make the header format a little better too. What's wrong with the IPv4 header? Well, we send a lot of information every packet that's not necessarily needed. Mainly, I'm talking about the fields used for fragmentation. Those fields only get used when the packet's fragmented, but we send those bits every time, so we're sending a bunch of zeros in there. So with IPv6, we have this idea of a base header, which only contains the minimum information needed to transmit the packet, and then we have extension headers that are used as needed. So as I said before with the fragmentation example, we're only sending what we need. So here's the base header format. We have the version, which will be 6 for IPv6. Traffic class and flow label, those are two things that can be done to expedite processing of packets or give a packet special treatment as far as quality of service. Payload length tells us how long the packet is. Next header tells us what the next header is. A hop limit, that's what used to be called the time to live. It actually is a hop count, right? The router decrements that by 1 every time a packet crosses it. So now we actually call it the hop limit. And then we have the source address and we have the destination address. And that is it for the base header format. The next header field is used to tell the computer or router what header is after this base header. So that's how we implement things like fragmentation or options that we'll talk about in a minute. So improve support for extensions and options. So based on using that next header field, if we need to add some new option or support a new protocol, we can simply add a new next header value, and then we can build that in. With IPv4, there was no way to add new options or add new things that weren't already built into the protocol, because that would involve everybody changing their implementation at the same time. So that makes extension of IPv6 more easily, that we can define that we have the next header field to point to what the next header is. So we can just create a new header for a protocol and define a new value for that field. So here's how that works. Say, for example, we have a normal packet. The top one's a normal TCP packet. It has a IPv6 base header, and then the next header says it's TCP, and then the next header is TCP. The next one below, we have the IPv6 base header, and then we have the next header says it's a routing header, and then we have the routing header second, and then after that we have in the routing header, the next header says TCP, and then we have the TCP header and data. And then finally the last one shows, hey, we can chain these headers together. Here we have an IPv6 base header, we have a routing header that says the next header is a fragment header, then we have a fragment header that says the next header is a TCP header, and then we have the TCP header and fragment of the data. So we can chain these different header fields together to get exactly what we need, and then we're not transmitting unnecessary bits around the internet all the time. So here are some extension headers that are defined: hop by hop options, routing, fragment, destination options, authentication, encapsulating security payload. Hop by hop options are options that are processed by each hop along the way. Routing, this was kind of like the source routing we talked about with IPv4, the source routing option. Fragment header is used when the packet needs to be fragmented. The minimum MTU for IPv6 is 1280 bytes, so that should limit the amount of fragmentation necessary in most of our Ethernet networks and whatnot. Destination options are options that are only processed by the final destination that receives the packet. Authentication, that's the authentication header part that's available with the IPsec protocols. It's an add-on to IPv4. It's built into IPv6. And encapsulating security payload, that's ESP. That's encrypting of the data, and that's, again, built into IPv6, where it's an add-on to IPv4. Flow labeling is a capability that lets us label packets belonging to particular traffic flows, and then we can give them special handling. So we can say, oh, hey, I want my voice traffic to be processed faster and be given more bandwidth. And then as the router processes the traffic, it pretty much puts this flow label in a table, and that way it doesn't have to process each packet looking up the destination address in the quality of service. It can just reference the flow label into the table after it's been added, and then it can process the packet much faster. Authentication and privacy, I talked about this. Authentication proves that the packet didn't change in transit. ESP provides encryption, and those are built into IPv6 where they were add-ons to IPv4. So how do we get from IPv4 to IPv6? Three strategies. You might run into dual stack. That's what you're most likely to see, where your PC has an IPv4 address and an IPv6 address. If you need to go to an IPv4 site, you use the IPv4 address. If you need to go to the IPv6 site, use the IPv6 address. Another option is tunneling. If an IPv4 packet needs to go across a network segment that is IPv6 only, the two routers will have a tunnel that they can encapsulate the IPv4 packet inside an IPv6 packet and send it across that segment of the network. And then header translation, there's some magic voodoo where you can take an IPv6 packet or an IPv4 packet and do some magic to make the IP addresses and all the header fields fit in as best as possible, and send the traffic across a router into different LAN using the other protocol. So why aren't we using IPv6? Well, there were three short-term remedies that were developed once we decided we needed IPv6 that allowed us to extend the life of the IPv4 address space. One of those was using network address translation, or NAT, along with private addressing. So now we don't necessarily need to have a public routable IP address on every host. So that limits the number of hosts of IP addresses that any particular network needs. Classless addressing also helped. If you recall, classful addressing, we gave out Class A addresses, Class B or Class A networks, Class B networks, and Class C networks, and that was our options. Well, so we gave lots of people, 2 to the 24 addresses for Class A, which is like a huge number. They didn't need that many addresses, and then we could give people 65,000 addresses for Class B, or 256. So with classless addressing, we can more carefully allocate addresses by giving people a number of addresses that more closely matches the number of addresses they need. And then DHCP, if we have 1,000 hosts around the world, in theory, we could only have the host using the addresses when the people are active and using those computers. So at nighttime, the hosts are turned off. They're not using a particular set of addresses. You could use those same addresses somewhere else by dynamically assigning them to the host. So if you have any questions, post them to the discussion board or bring them to class.